This is a map of 18th century Königsberg. In the center of the city, 7 bridges connect 2 islands to the mainland and to each other. For the people living here, these bridges were the basis of a local riddle. Is it possible to walk through the city and cross every single bridge exactly once? Solving this by walking was a matter of trial and error. But even for a small area, the number of possible routes is high enough that it is difficult to be certain you haven't missed a combination. At the time, mathematics offered no shortcut. Geometry was built on the Euclidean principles of measuring physical distances and angles, none of which determine whether a specific path is possible across a network. You could walk a specific path and show that it failed, but without a new way to model the problem, you couldn't prove that every other possible path would fail too. While Euler considered the bridge puzzle, the wider mathematical community was struggling with a similar problem of scale in calculus and analysis. This was the syncopated era of math. Instead of the clean equations we use today, mathematicians often described their work in long, rhetorical paragraphs, using shorthand words to represent operations. This wordy approach was a burden on working memory. As the concepts became more complex, the time spent reading and parsing the descriptions made it harder to actually perform the calculations. Both the bridge puzzle and the development of calculus were hitting a limit. The tools available were too descriptive and not abstract enough to handle complex relational structures. Leonhard Euler initially found the bridge puzzle trivial, but he realized it required a type of analysis that didn't yet exist, a geometry of position that ignored physical magnitude. To solve it, he stripped away everything that didn't contribute to the answer. He realized the width of the river and the length of the bridges didn't matter, so he deleted them from his model. He reduced the landmasses to dimensionless dots, or vertices, and the bridges to simple lines, called edges. This was the first formal mathematical graph. In this model, if you enter a vertex, you must also leave it. Every bridge you use to arrive must be paired with another bridge you use to depart. This means a continuous path only exists if the number of edges touching a vertex is even. The only exceptions are the start and endpoints. But in Königsberg, the vertices have 3, 3, 3, and 5 edges. They are all odd. By ignoring the physical map and focusing on the connections, Euler proved the walk was impossible. In the process, he established the foundations of modern graph theory. Euler applied this same strategy of removing descriptive noise to the way math was written on the page. His 1748 textbook, Introductio in Analysisem Infinitorum, became the primary tool for standardizing a new symbolic language across Europe. Just as he replaced islands with dots, he replaced long descriptions with symbolic shorthand. He popularized the f of x notation for functions and the Greek letter sigma for summations. He introduced the symbol e, the imaginary unit I, and the constant pi. These weren't just abbreviations, they were precise, universal markers that allowed mathematicians to communicate across different languages. By reducing the visual space an operation took up on the page, Euler increased the amount of information a mathematician could process at once, allowing for much more complex analysis. Euler's work showed that the most important properties of a system are often found in its connectivity rather than its physical appearance. This perspective is the underlying framework for how modern digital systems handle information. When you use a navigation app or a shipping service, the underlying software is using Euler's graph theory to find a path through a network of millions of abstract vertices and edges. Today, researchers use these same principles in graph neural networks to analyze everything from social media interactions to the way molecules are structured. Euler's solution to a minor bridge puzzle suggested that the most effective way to understand a complex system is to stop looking at what things are and focus entirely on how they are connected.